Well, here it is, the moment you never thought would come, the very last video for advanced physics. You might need to go grab some tissues. I'm sure you're going to have some tears by the end. You'll be so sad to not have any more videos to watch. But we do have some pretty cool stuff to talk about in this one. First of all, this guy right here, his name was James Clerk Maxwell. He was a Scottish physicist, and he was pretty amazing. A lot of people put him up there with Newton and Einstein as one of the best physicists of all time. And not only did he give us these wonderful equations for electromagnetism, he contributed to all kinds of things like the kinetic theory of gases. He also was the first to explain Saturn's rings, how they could be a stable structure, that they were chunks instead of these solid objects that they thought they were. But anyway, props to James Clerk Maxwell. Now, let's look at his equations. We've actually been using most of these throughout the year. These over here, I'm going to put a dividing line, these are the exact same equations just converted into what we call differential notation, whereas these are integral notation. To convert them, for these two, you use what is known as the divergence theorem, which is kind of a generalized form of the fundamental theorem of calculus. For these ones, to convert them, you use what's known as Stokes' theorem, which is kind of related to that as well. But it gets a little more complicated when you're dealing with 3 dimensions and line integrals and surface integrals and all of these things. But let's look at these guys over here. We've seen this one before, E dot dA. So this tells us how the charge distribution relates to the electric field, and this is our good friend known as Gauss's law. This next one here we haven't seen before, and it is known as Gauss's law of magnetism. And you might wonder, well, what kind of equation is this? It's just equal to 0. And the reason for that is because we can't find any magnetic monopoles. If we did find magnetic monopoles, we would take some quantity similar to charge, Q, and this would be equal to whatever that quantity is. But until we find magnetic monopoles, it's just equal to 0. Now, this equation is useful in certain situations, but not in the things we looked at this year. Okay, the next one is another equation that we know and love that tells us if we have a changing magnetic flux, that gives us an electric field, which leads to induced EMFs and induced currents and all of these wonderful things. And this was known as Faraday's law. Faraday's law. Now this last one, we've seen this portion of it, and it tells us that currents create magnetic fields. And this one was known as Ampere's law. So you might have a couple of questions at this point. First of all, what is this thing doing here? Well, that's one thing that we'll go over in this video. We'll explain that. And your other question might be, well, if all of these things were discovered by these other guys, at least they're named after them, so we assume they were discovered by them, what the heck does Maxwell have to do with anything? Well, he was the first to kind of gather them and kind of change their forms a bit and make them all nice and uniform. He did actually contribute this little piece here, which is important to unifying the overall ideas. But yeah, some people argue, he didn't do so much. But in another sense, he unified these ideas, which was huge. This was a big influence on Einstein. That's why Einstein spent most of his life trying to find a unified theory, because he thought this was the most elegant, amazing thing that you could do. Okay, let's get to this little addition here, the Maxwell's correction. Ooh, I don't know why I did that. Maxwell's correction to Ampere's law. So Ampere's law told us that if we have some closed path, then we could take the integral b dot dl around that closed path, and that will always equal or be proportional to the enclosed current going through a surface bound by that path. Now, we could have several surfaces bound by that ring. You could have the obvious one, which is this nice flat circular area here, and the current is going through that surface, so yeah, that works. But you could also create this kind of pouch surface here, where you don't have surface 1 at all. You just have a ring and then a pouch. That pouch is a surface still bound by that closed path, so this equation still has to hold. And in this case, the current does go through that pouch, just like it goes through that surface, so you can still use this part of the equation without any problems. But here is a situation where we do run into problems. Sorry, I've got a bit of a runny nose. I think it's allergies. I looked up and tree pollen is high this time of year, so I'm guessing I have some allergies to yeah, I'm allergic to tree pollen. Okay, here is our path. We could have this closed, well, we got a closed path. We could have this surface here bound by that path, in which case the current is flowing through it. This is a capacitor that is discharging, by the way, because the current is flowing away from the positive side. So here I would get my enclosed current. But what if I use this pouch-like surface instead that goes around the capacitor? We know that no current flows in between the plates of a capacitor. So now I'm not changing the closed loop I have on the left-hand side of this equation, but if I change the surface, now I would say that the enclosed current is 0, and that's going to be a contradiction, because this is not going to be 0, and that is, and you're going to have a problem here. So what Maxwell did is he added this term here, and this accounts for this situation, which you might think, well, this is just kind of an odd situation. Why do we really care? But if you look at this, this tells us the rate of change of the electric flux gives us a magnetic field. And this is nice and elegant, as the theoretical physicists would say, because we saw earlier that a changing magnetic flux produces an electric field. Now we can see also that a changing electric flux produces a magnetic field. So this gives us a nice symmetry, a nice unity to the way we think the laws of electromagnetism work. Now I'll show you where this comes from. Since we're dealing with a capacitor, we can say that Q on that capacitor is equal to CV. We also know that for a capacitor where we have a constant electric field, we can say that V equals ED. And we also know that the capacitance is epsilon naught A over D. So if I substitute in these two things to this equation here, I've got epsilon naught A over D times the electric field times D. These two D's are the same thing, so I get Q equals epsilon naught AD. Now this part here was a current, and essentially we want to treat this like a type of current. So if I do dq dt, which is equal to current, then I'm going to get epsilon naught A is constant, but my electric field might not be, so that's going to be dE dt. If I go ahead and pull that A in there, then the AE becomes the electric flux. I guess I could combine them ahead of time. That's all right. So you get epsilon naught times the derivative of the electric flux with respect to time. Now this is a current, so I have one current here. Essentially, a lot of times we write this as the regular current or the conduction current plus this other current here, which I'll put a subscript D. This is sometimes known as the displacement current. For what reason, I have no idea. It doesn't really apply to displacements, but anyway, so these are they both have to be enclosed in our surface thing here. So since this guy's a current, we multiply it by mu naught. So we take this guy and we just distributed that mu naught to those two currents. So this guy right here is my displacement current. So writing that all out a little more nicely, here is Ampere's law in the long form. You can write it in shorthand notation like this, where we just take into account two different types of current now, the one that we're normally familiar with and this new type of displacement current, which is equal to the rate of change of the electric flux, the time rate of change. Okay, now, as I mentioned earlier, this little addition gave Maxwell the clue that a changing electric field produces a changing magnetic field, and a changing magnetic field produces a changing electric field. So once you get two oscillating fields, electric and magnetic, they could potentially sustain each other and just keep propagating through space, because one is producing the other and vice versa. And so it would be self-propagating. To animate it, it would look something like this, where you have, if you look at a single point here, the fields are going up and down and in and out at that point, and it propagates off in that direction. And so he called this an electromagnetic wave, because you have an electric field and a magnetic field self-sustaining. Pretty cool. Then he did some other calculations to find the speed of this thing. You probably know the end of the story, but it's still a good story anyway, and we're going to tell it. So, if I define the electric field, it's a sinusoidal function. So, in this case, we're just going to look at the vertical component of the electric field, which is going to be the maximum value of the electric field times a sine function. Now, what is this kx thing? We're used to having omega t's in our sine and cosine functions for oscillating system. Well, this k here is what we call the wave number. Essentially, it's like the spatial frequency. Okay, so omega is like the temporal frequency, or the frequency in time, and this is like the frequency in space. So if this wave is moving, omega t is telling you how quickly it's moving, but if you take a snapshot for a constant value of t, this k is going to tell you about the wavelength in space. Well, the inverse wavelength. It's like the frequency in space. Okay, so it's related to wavelength by a factor of 2 pi. So k is 2 pi over lambda. Omega is 2 pi over f. If you multiply those things, we had this relationship earlier when we studied waves, that v equals f lambda. It's also omega over k is also equal to v, and that's going to be important later on in some of our analysis. This is waves per time, and this is waves per space, which works out to be, brings the space up top, and so it's space per wave, or distance per, or sorry, space per time, or distance per time, which is velocity. Alright, so now we're going to start applying some of our equations to this. We're going to start out with E dot dl is equal to the rate of change of magnetic flux. You don't have to copy all of this down. You can, but okay, so we have Faraday's law here, and we're going to apply that to a loop going around in the plane of my electric field here. Okay, so since we have a dot product, these segments right here and right here, dl is perpendicular to the E field, and the dot product wants the parallel component, so those parts go to 0. So we just need to worry about the vertical parts here. Now they have the same length, but the E field is stronger here than it is here. So if we multiply the E field by the length, I'm going to call that length delta y. For the stronger E field, I'm going to say that it is E plus a little bit, and I'll explain that here in a second, times delta y minus E delta y. Okay, so this is the left-hand side of my expression here. So the minus E delta y is this side, where they're anti-parallel, so that's why I get a negative sign. And we'll say that the field has a value of E here, and dl evaluates to delta y. Over here, the field is a little bit higher here than here, and so it's got the same amount. Essentially, I'm calling the difference in the field here dE. Now don't confuse this difference here with an actual distance. I'm talking about the magnitude of the field. It's not a spatial distance. Okay, so the field is a little bit bigger on the right-hand side of that rectangle than on the left-hand side. Okay, now on this side, we're going to get negative dB dt times dx dy, because we're pulling out the area. Essentially, this was d by dt of b times the area, and so I just wrote the area as the width times the height. So we've got a dx here and a dy. Okay, I guess these should have been deltas, but yeah, there you go. So the delta y's go away, and then I've got an E minus E here, so that goes away, and I end up with a dE equals negative dB dt times dx, and if I divide that dx to the other side, I get this. And since this wave is a function of space and time, these should technically be partial derivatives. So we have the partial derivative of the electric field with respect to space is equal to the partial derivative of the magnetic field with respect to time. And I'm just going to box this up So if we go ahead and take these equations here and take the derivatives with respect to x and t and plug those in here, first of all we'll get dE dx, which is going to get a k coming out of that derivative. We've got E naught, which is the maximum value of the electric field. Our sign becomes a cosine, and then we still have kx minus omega t on the inside. Okay, for the other side of this equation, we want the derivative of b with respect to t. I'm just going to go ahead and write it right here. So taking the derivative with respect to t is going to pull out a negative omega. Since we already had a negative out there, the negative will go away, and we're left with omega b naught cosine kx minus omega t. And the nice thing is these cosine functions go away. And if we rearrange this, we can solve for the ratio of the max E field to the max B field is going to equal the ratio of omega to k. And we can actually get rid of the max parts, because since they're in phase, this ratio will be constant at all times. So we can just say more generally that the ratio of the E field to the B field at any moment is going to equal omega over k. And I mentioned that that was going to be important earlier, because if we look over here, omega over k tells us that this is equal to the velocity of the wave. Now we don't know necessarily what E and B are yet, so we don't have the speed of the electromagnetic wave figured out quite yet, but this is another important relationship that we will come back to. Alright, now we're going to look at the B field portion, and here we're going to use integral of b dot dl is equal to mu naught epsilon naught d phi dt, where we got rid of the mu naught I enclosed, or the mu naught I for the conventional current, because there are no currents where this electromagnetic wave is traveling. You need wires and stuff to have currents. So we got rid of the part of Ampere's law that we knew best, and we're using this new part here that Maxwell gave us. And we're going to follow a similar process. So here on the way out, I'm going to take the smaller value of b though. So I'm going to have b times delta z, where delta z is the length out here in the z direction, minus, when we're coming back in the loop here, now here I've got the bigger magnetic field, so I'm going to say b plus dB is the magnitude of that magnetic field, again times delta z. On the other side of the equation we've got mu naught epsilon naught, and then we're going to have dE dt times the area, and the area in this case is going to be delta z times dx. So similar to what we saw last time, z's go away, these b's are going to go away, and I end up with dB equals, I got a negative sign here, mu naught epsilon naught dE dt, and then I'm going to have a dx on the end here. I might as well throw that over here just to make it nice. And now we'll do what we did before. We're going to take the derivative of the B field with respect to x this time. And I've got a negative here, so I'm going to get, pulls out a k, and then I've got a b naught, becomes cosine kx minus omega t. Still have my constants out in front here. And then dE dt, this is going to pull out a negative omega. I'll put the negative sign up there, and then I've got omega E naught cosine of all of this stuff. Again, the cosine parts go away. We can get rid of the negatives, and we can get E to B ratio again. And that's going to leave us, let's see, I moved the b over here, so that's going to leave me with a k over here, all over mu naught epsilon naught omega. Now I've got k on omega, so I'm going to get, I can make that into a velocity. So 1 over mu naught epsilon times the velocity down here. We can do the same thing where we can get rid of the max values here, because this is going to be true. at any moment in time. Now if we combine this with the other expression we had, we said that E over B was equal to V, and now we're saying it's equal to this. So both V and this thing are equal to E over B, so we can set those things equal to each other. So we can say V is equal to mu naught. Can you guys feel it building up to an amazing discovery? So if we pull the V over here, we get V squared is equal to 1 over mu naught epsilon naught, and V, I'm going to come over here, is equal to the square root of 1 over mu naught epsilon naught. Beautiful equation expressing the velocity of the electromagnetic wave just in terms of these fundamental constants that tell us something about how the electric field and the magnetic field propagate through space, right? That's how we've seen them all year long. Now if we go ahead and calculate the value for this, so we're going to put in 4 pi times 10 to the negative 7th times 8.85 times 10 to the negative 12th. You throw that in your calculator, drum roll. Guess what you get? You get 3.0 times 10 to the 8th, and the units work out to be meters per second. So Maxwell did this calculation, probably not the exact way we did it, but something similar, and he saw that and he was like, holy crap, light is an electromagnetic wave. Woohoo! I am the greatest scientist, or at least in the top 3 of all time. So there you have it, folks. Never forget it. Wonderful, beautiful physics.